Picture this. You take a normal, room temperature thermometer and just dunk it straight into a pot of rolling, boiling water. Now, ask yourself, why doesn't that little red line instantly teleport to 100 degrees Celsius? I mean, it takes a sec, right? It shoots up super fast at first and then kind of slows down right as it gets closer to the actual temperature. That simple, everyday delay you're seeing, that is actually the gateway to one of the most fundamental concepts in engineering, because in the physical world, absolutely nothing changes instantly.
Welcome to this explainer. Today, we're going to completely demystify the math behind dynamic systems. Look, if you're an engineering or tech student, staring at a massive wall of differential equations can honestly feel pretty overwhelming. But we're going to cut through all that noise today. We're focusing purely on the core parameters that give physical processes their totally unique behaviors. By the end of this, you're going to see exactly how you can predict the future of a system using just a couple of ridiculously simple variables.
Here is our roadmap for today. We'll start with the dynamics of change, break down first-order systems, look at time constant and gain, see how second-order systems emerge, talk about the damping factor, and then wrap it all up with controlling real-world processes.
All right, part 1, the dynamics of change. Let's establish a foundational rule right out of the gate. Whether it's that thermometer getting used to a cold room, a massive industrial tank filling up with liquid, or even your car's suspension bouncing after you hit a speed bump way too fast, the physical world simply takes time to catch up. A system literally cannot match a new input instantly without going through a transition period first. There's always this transient state before things finally calm down into a steady state. And our entire job as engineers? Figure out exactly how to map that transition.
Moving right along to Part 2, First-Order Systems Explained.
We're starting with the absolute simplest form of dynamic change, the single exponential stage. Now, when you look at a standard textbook breakdown of the operational transfer function, it is incredibly easy to get bogged down in all the heavy differential calculus, all the dx by dt's and various constants, but actually scratch that. If we strip all the heavy math away, we can just focus on the parameters that give the system its actual real-world personality. For these first-order systems, it all boils down to the time constant, tau, and the static sensitivity, or gain. Which brings us nicely to Part 3, time constant and gain. So, for a straightforward first-order system, like our thermometer or a basic mixing tank, its whole vibe is defined by just two crucial parameters. The first one is the time constant, represented by the Greek letter tau. You can basically think of tau as the system's speed limit. It dictates exactly how fast the system gets to its final destination after a step disturbance, like, say, suddenly cranking up a heater. A really small tau means you've got a very snappy, lightning-fast response. A massive tau? Yeah, that system is going to be super slow and sluggish.
And guys, here is an absolute cheat code for your exams. Seriously, lock this into your memory. If you look at the step response of literally any first-order system at a time exactly equal to one time constant, when time equals tau, the system has completed exactly 63.2% of its ultimate response. That is a perfect universal metric. If a thermometer takes 10 seconds to reach 63.2% of a temperature change, boom, you instantly know its time constant is exactly 10 seconds.
Now, while the time constant tells us how fast we're driving, the second parameter tells us where we're actually parking. The steady-state gain, or Kp, simply tells us how far the system is ultimately going to go once it settles into its new steady state. It's just the ratio of the ultimate change in output divided by the change in input. So, if you open a valve by 10% and the flow rate eventually jumps up by 20 gallons per minute, 20 divided by 10, your gain is 2. It really is that simple.
But let's step it up a notch and see how this plays out in more complex realities. First-order systems, they smoothly rise using basically just that one dynamic parameter for speed, tau. But what on earth happens when a system has physical inertia, like a giant mechanical spring? Or what if you've got multiple capacities stacked up in series, like fluid draining from one tank directly into another? Well, a simple smooth curve just doesn't cover it anymore.
And that's exactly why we have Part 4, second-order systems emerge.
This is where the math gets a very necessary upgrade. The denominator of our standard transfer function expands. Now, we still keep a time constant, tau, which in this case represents the natural period of oscillation. But right next to it, we're throwing a second dynamic parameter into the mix. This new guy is called the damping factor, represented by the Greek letter zeta.
Let's dive deep into Part 5, the damping factor.
The damping factor, zeta, is honestly the absolute main character of the show here. If tau is your speed limit, zeta acts exactly like the shock absorbers on a car. It determines exactly how the system handles the sheer energy of a sudden change. Is it going to bounce all over the place? Will it hit the target super smoothly? Or is it going to take forever to finally settle? This one single parameter dictates the entire personality of the system, breaking down into 3 specific states. First, if zeta is less than 1, this system is underdamped. It's highly oscillatory. It's going to wildly overshoot the target and bounce up and down before it finally settles. Second, if zeta is exactly 1, it's critically damped. It hits the target perfectly, as fast as physically possible, with absolutely zero bouncing. And third, if zeta is greater than 1, it's overdamped. It just drags its feet sluggishly on a long, slow path to the final value.
When you look at the dynamic error equations, you quickly realize the damping ratio is the ultimate predictor. Whether we're dealing with a pressure gauge that has a damping ratio of 0.5, which instantly tells us it's going to bounce like crazy, or a heavy thermal element that's super overdamped, we just plug our zeta and tau right into these formulas. We never have to guess if our instrument is going to give us a clean reading. The math literally tells us exactly how much dynamic error we're going to face.
Bringing us to our final stop, Part 6, Controlling Real-World Processes.
Now, as tech and engineering students, you might be thinking, if inherently second-order systems are actually pretty rare in nature, why are we obsessing so much over zeta? Well, it's because of the reality out there in the field. Almost every complex multi-stage process you'll ever encounter actually starts behaving exactly like a second-order system the very second you attach a controller to it. Think about it. When you hook up a sensor, a transmitter, and an automated valve to a simple first-order tank just to control the liquid level, you have just created a closed-loop system. And that system, it can now overshoot, it can oscillate, it can bounce. Bam, you have essentially introduced second-order dynamics into the world all on your own.
Which leaves us with this final thought for today's explainer. By stripping away all the intimidating calculus and just focusing squarely on tau, the gain, and the damping factor zeta, you literally hold the keys to how physical systems react in real time. If understanding just these core parameters allows us to predict complex bouncing physical behavior, how are you going to use them to tune and perfect your own engineering designs? Because mastering these concepts doesn't just help you pass a midterm, it literally gives you the ability to control the physical world. Keep analyzing, keep calculating, and I'll catch you guys in the next one.